In 2012, physicists announced the discovery of the Higgs boson, and the world celebrated. Headlines declared the mystery of mass had been solved. The missing piece of the puzzle had finally been found. But here is what almost nobody talks about. The Higgs boson was supposed to explain why things have mass, and yet, after its discovery, mass remains one of the deepest unsolved problems in all of physics. The proton, the thing that gives most of your body its weight, gets almost none of its mass from the Higgs field. The specific masses of every fundamental particle are still unexplained. And the Higgs boson itself has a mass that, according to our best theories, shouldn't even be possible without an almost miraculous cancellation. The discovery wasn't a failure. It was something stranger. It was a door that opened onto an even bigger mystery. If you find this kind of deep exploration of physics interesting, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference for me. Now, let's begin. Pick up anything near you. A phone, a book, a cup of water. Feel the weight of it in your hand. That sensation, that pull toward the ground, comes from mass. Mass is what makes matter feel like matter. It is the reason your feet press against the floor, the reason a truck is harder to push than a bicycle, the reason stars collapse under their own gravity and planets hold on to their atmospheres. Mass seems like the simplest, most obvious property in the universe. Everything has it, or at least everything you can touch and hold. You have been experiencing mass your entire life. Every single moment, gravity has been acting on your mass, pulling you down, keeping you anchored to this planet. You have never known a single instant without it. And yet, for most of the 20th century, physicists could not explain where mass comes from. Not in any deep sense. They could measure it. They could use it in equations. They could predict how objects with a given mass would behave. But when they tried to build a fundamental theory of nature, a theory that explained how particles interact at the deepest level, they ran into a devastating problem. Their equations only worked if every fundamental particle was massless. Not light, not small, completely massless. Zero mass, moving at the speed of light with no inertia whatsoever. This was not a minor technical glitch, it was a catastrophe. Because particles obviously do have mass. Electrons have mass, quarks have mass. The particles that carry the weak nuclear force have mass. Reality was telling physicists one thing, and their best mathematical framework was telling them the opposite. To understand why this was such a crisis, and how the Higgs field eventually resolved it, you need to understand what modern particle physics actually is. Because the picture most people carry around in their heads, the image of tiny little balls bouncing off each other, is wrong. It is not even close to what physicists mean when they talk about particles. In modern physics, the fundamental entities are not particles. They are fields. A field is something that exists everywhere in space, at every single point, all the time. You are already familiar with some fields, even if you have not thought of them that way. The gravitational field exists everywhere around Earth. It tells objects which direction to fall and how strongly. The electromagnetic field exists everywhere. It carries light, radio waves, microwaves. When you see a rainbow or feel warmth from the sun, you are experiencing the electromagnetic field in action. In particle physics, every type of particle corresponds to a field that fills all of space. There is an electron field permeating the entire universe. There is an up quark field, a down quark field, a photon field. Each of these fields can be excited, and when a field is excited in a particular way, that excitation is what we detect as a particle. An electron is not a tiny ball sitting in space. It is a localized vibration in the electron field, a ripple in something that stretches across the cosmos. A photon is a ripple in the electromagnetic field. Every particle you have ever heard of is a ripple in its corresponding quantum field. This is quantum field theory, and it is the foundation of all modern particle physics. It is the most precisely tested framework in the history of science. Its predictions have been confirmed to extraordinary accuracy. sometimes matching experiments to better than 10 decimal places. Now, within this framework, physicists built something called the Standard Model. This is the theory that describes all known fundamental particles and 3 of the 4 fundamental forces: the electromagnetic force, which governs light and holds atoms together; the strong nuclear force, which binds quarks inside protons and neutrons; and the weak nuclear force, which governs certain types of radioactive decay and plays a role in how the sun generates energy. The Standard Model is not a guess. It is not a rough sketch. It is one of the most successful theories in the history of science. Every particle it predicted has been found. Its calculations match experimental results with staggering precision. If the Standard Model were a bridge, it would be engineered to tolerances finer than the width of an atom. It works phenomenally well. But there was a problem at its heart, and that problem had to do with mass. In the 1960s and 70s, physicists including Sheldon Glashow, Abdus Salam, and Steven Weinberg developed a unified theory of the electromagnetic force and the weak nuclear force. This was a major intellectual achievement. 2 forces that seemed completely different: electromagnetism, which has infinite range, and the weak force, which operates only at subatomic distances, turned out to be 2 aspects of the same underlying force. At very high energies, the kind of energies that existed shortly after the Big Bang, these 2 forces would have been indistinguishable. They were one force, the electro-weak force. But this unification came with a requirement. The mathematical structure that made it work, a type of framework called a Yang-Mills gauge theory, demanded that the particles carrying the force had to be massless. All of them. The photon, which carries the electromagnetic force, is indeed massless. That checks out. But the particles carrying the weak force, called the W and Z bosons, are extremely heavy. The W boson has a mass of about 80.4 giga-electron-volts, and the Z boson has a mass of about 91.2 giga-electron-volts. These are among the heaviest fundamental particles known. They are roughly 85 to nearly 100 times heavier than a proton. This was the crisis. The theory that unified 2 fundamental forces, a theory that was elegant and beautiful and mathematically consistent, required its force-carrying particles to be massless. But reality said those particles were massive. If you just forced mass into the equations by hand, the whole mathematical structure collapsed. The theory became inconsistent. It produced nonsensical predictions, like probabilities that exceeded 100%. It generated infinities that could not be controlled. The theory broke. So physicists had a choice. Either the electro-weak unification was wrong, or there was something else going on. Some hidden mechanism that was giving these particles mass in a way that preserved the mathematical consistency of the theory. This is where symmetry comes in, and understanding symmetry is essential to understanding what the Higgs field actually does. Symmetry in physics does not just mean that something looks the same on both sides, like a butterfly's wings. It means something deeper. A symmetry is a transformation you can perform on a system without changing the underlying physics. If you rotate a perfect sphere, it looks the same from every angle. That is rotational symmetry. If you move your physics experiment from one laboratory to another, the laws of physics work the same way. That is translational symmetry. The electro-weak theory has a specific mathematical symmetry called gauge symmetry. This symmetry is what makes the theory work. It is what ensures the theory is mathematically consistent, that calculations give finite answers, that probabilities add up correctly. Gauge symmetry is not optional. It is the backbone of the theory. Without it, the mathematics falls apart. But here is the crucial point. Gauge symmetry, in its unbroken form, requires the force-carrying particles to be massless. A mass term for the W and Z bosons would explicitly violate the gauge symmetry. It would be like adding a lump to a perfect sphere. The symmetry would be destroyed, and all the nice mathematical properties that came with it would vanish. What physicists needed was a way to give particles mass without destroying the symmetry. And the solution turned out to be one of the most ingenious ideas in the history of physics. You do not destroy the symmetry, you hide it. This concept is called spontaneous symmetry breaking. The idea is that the laws of physics can have a symmetry, but the state the universe actually settles into does not display that symmetry. The symmetry is still there in the equations, it is still there in the fundamental laws, but the actual physical situation, the ground state of the universe, does not reflect it. Here is an analogy that might help. Imagine a ball sitting perfectly balanced on top of a hill. The hill is perfectly symmetric. Every direction downhill looks exactly the same. The ball at the top respects this symmetry. It is not pointing in any particular direction. But this situation is unstable. The ball will roll down the hill, and when it does, it has to pick a direction. It rolls north or south or east or west. The hill itself is still symmetric. Nothing about the hill has changed, but the ball's final resting position at the bottom of the hill breaks the symmetry. It is sitting in one specific spot, pointing in one specific direction, even though no direction was special. The laws governing the ball are symmetric, but the actual state of the ball is not. The symmetry is hidden. It is still there in the equations, but it is not visible in the outcome. This is what happens with the Higgs field. The laws of physics have the full electroweak gauge symmetry. But the Higgs field, instead of sitting at zero like most fields in their lowest energy state, settles into a non-zero value everywhere in the universe. It is like the ball rolling off the top of the hill. The field picks a particular value, and that value breaks the symmetry. Not by destroying it, but by hiding it. The symmetry is still there in the fundamental equations, but it is not manifest in the universe we observe. The idea that a field could break symmetry this way was developed in the early 1960s by several groups of physicists working somewhat independently. In 1964, 3 separate papers proposed the mechanism. One was by Peter Higgs, another was by François Englert and Robert Brout. A third was by Gerald Guralnick, Carl Hagen and Tom Kibble. All 3 groups recognized that a scalar field, a field with no intrinsic spin or direction, could acquire a non-zero value in its ground state and break the gauge symmetry spontaneously. The idea drew on earlier work by Yoichiro Nambu on symmetry breaking in particle physics and by Philip Anderson on similar phenomena in condensed matter physics, where symmetry breaking explains superconductivity. So what does the Higgs field actually do? It fills all of space with a non-zero background value. Think of it as an invisible medium that permeates everything. Every particle moving through the universe is moving through this field. And certain particles interact with it. The W and Z bosons interact very strongly with the Higgs field. As they move through the universe, they are constantly interacting with this background field, and that interaction slows them down, gives them inertia, gives them mass. The stronger a particle's interaction with the Higgs field, the more mass it acquires. The weaker the interaction, the less mass. Photons do not interact with the Higgs field at all, which is why photons are massless. They pass through the Higgs field without noticing it. This mechanism also works for the fundamental fermions, the matter particles. Electrons, quarks, muons and taus all acquire their masses through their interaction with the Higgs field. This interaction is described by what physicists call Yukawa couplings, named after the Japanese physicist Hideki Yukawa. Each fundamental fermion has its own coupling strength to the Higgs field, and that coupling determines its mass. The electron has a small coupling, so it has a small mass. The top quark has an enormous coupling, the largest of any known particle, and it is the heaviest known fundamental fermion. The beauty of this mechanism is that it gives particles mass without destroying the gauge symmetry that makes the electroweak theory work. The symmetry is still there. It is still doing its job, ensuring the theory is mathematically consistent. It is just hidden by the Higgs field's non-zero value. The equations still possess the symmetry. The universe just does not display it. Now, there is an important consequence of this mechanism. If the Higgs field exists and has a non-zero value everywhere, then it should be possible to create a ripple in that field. Just as you can create a ripple in water by disturbing its surface, you should be able to create a ripple in the Higgs field by pumping enough energy into it. That ripple, that excitation, would appear to us as a particle, a new particle, the Higgs boson. The Higgs boson is not what gives other particles mass. That is a common misconception. The Higgs field is what gives particles mass. The Higgs boson is a vibration in that field. It is the evidence that the field exists. Finding the Higgs boson would be like finding a wave on the surface of an ocean you suspected was there but could not see. The wave proves the ocean is real. For nearly half a century after the mechanism was proposed in 1964, physicists searched for this particle. They built increasingly powerful particle accelerators, smashing particles together at higher and higher energies, hoping to create enough energy in a small enough region to excite the Higgs field and produce a Higgs boson. The search was difficult because the theory did not predict exactly what mass the Higgs boson should have. Physicists knew it existed somewhere, but they did not know precisely where to look. Experiments at CERN near Geneva and at Fermilab near Chicago gradually narrowed the range of possible masses. They ruled out large regions of parameter space, eliminating masses that were too low or too high. By the early 2000s, the search had narrowed considerably, and a new machine was being built that would have enough energy to either find the Higgs boson or prove it did not exist in the expected mass range. That machine was the Large Hadron Collider, the LHC, the largest and most powerful particle accelerator ever constructed. It sits in a circular tunnel about 27 kilometers in circumference, roughly 100 meters underground, beneath the border between Switzerland and France. Inside that tunnel, two beams of protons circulate in opposite directions, accelerated to nearly the speed of light. When the beams collide, the energy of the collision can create new particles, including, if the energy is high enough, a Higgs boson. On July 4, 2012, two independent experiments at the LHC, called ATLAS and CMS, announced that they had both observed a new particle consistent with the Higgs boson. The measured mass was approximately 125 giga-electron volts. The statistical significance was overwhelming. This was not a fluke. This was not a statistical fluctuation. Both experiments, using different detectors and different analysis methods, found the same particle at the same mass. The probability that this was random noise was less than 1 in 3 million for each experiment independently. The Higgs boson had been found. The reaction in the physics community was extraordinary. Peter Higgs, then 83 years old, was in the audience at CERN when the results were announced. He wept. François Englert was also present. Robert Brout had passed away the year before, never seeing the confirmation of the mechanism he helped create. In 2013, Higgs and Englert were awarded the Nobel Prize in Physics for their theoretical prediction. The discovery confirmed that the Higgs field is real. It is not a mathematical trick or a convenient fiction. It is a physical field that permeates the entire universe, giving mass to the W and Z bosons and to the fundamental fermions through their interactions with it. The mechanism that was proposed on paper in 1964 was validated by experiment in 2012. The electroweak theory, with its hidden symmetry and its Higgs mechanism, was correct. This was genuinely one of the great triumphs of human intellectual achievement. A mechanism dreamed up by a handful of theorists nearly 50 years earlier, based purely on mathematical reasoning and physical intuition, was confirmed in a machine that took decades to design and build, cost billions of dollars, and required the collaboration of thousands of scientists from dozens of countries. The standard model, the most detailed and precise theory of nature ever constructed, was complete. Every particle it predicted had now been observed. But here is where the story takes a turn that most people do not expect. Confirming that the Higgs mechanism exists is not the same thing as explaining mass, not even close. The Higgs mechanism tells you how particles acquire mass. It tells you the process, the machinery, the steps. A particle interacts with the Higgs field. That interaction gives it mass. Fine, but there is a question the mechanism does not answer, and it is perhaps the most obvious question you could ask. Why does each particle have the specific mass it has? The electron has a mass of about 0.511 mega-electron volts. The muon, which is essentially a heavier version of the electron, has a mass about 207 times larger. The tau lepton is about 3,482 times heavier than the electron. The top quark has a mass of about 173 giga-electron volts, roughly 340,000 times the mass of the electron. Why? Why these numbers? Why is the electron so light and the top quark so heavy? Why is the muon 207 times heavier than the electron and not 200 or 300 or 50? The Higgs mechanism has no answer. The coupling strengths between each particle and the Higgs field, those Yukawa couplings that determine each particle's mass, are not predicted by the standard model. They are free parameters. They are numbers that physicists have to measure in experiments and then plug into the equations by hand. The theory accepts any value. It does not prefer one over another. It does not explain why the numbers are what they are. It just says that whatever the coupling is, that determines the mass. But it does not tell you what the coupling should be. This is like discovering that a piano produces sound through vibrating strings, but being unable to explain why each string is tuned to a particular note. You understand the mechanism. You know that string tension and length determine pitch, but you cannot explain why someone tuned the piano the way they did. The machinery runs, but nobody chose the settings. And this is not a small gap. The masses of the fundamental particles span an enormous range. The lightest known particles with mass, the neutrinos, have masses at least 1,000,000 times smaller than the electron. The heaviest fundamental particle, the top quark, has a mass roughly 340,000 times larger than the electron. That is a range covering at least 12 orders of magnitude, 12 powers of 10, from the lightest to the heaviest. The standard model treats every single one of these values as an arbitrary input. It shrugs and says, that is just how the universe is. The Higgs mechanism was supposed to explain mass, and it does, in a sense. It explains the process by which mass arises, but it does not explain the pattern. It does not explain why the universe has the specific set of masses it has, rather than some completely different set. The discovery of the Higgs boson confirmed the mechanism, but it left the deeper question of mass completely untouched. And as we are about to see, the mystery goes even deeper than unexplained coupling strengths. Because most of the mass you experience every day, the mass of your body, the mass of the chair you are sitting in, the mass of the planet beneath your feet, does not come from the Higgs field at all. Think about your own body for a moment. You have mass. You can step on a scale and measure it. That mass is what keeps you planted on the ground, what makes it take effort to stand up from a chair, and what gives you momentum when you run. Your body is made of cells, and those cells are made of molecules, and those molecules are made of atoms, and those atoms are made of electrons orbiting a nucleus. The nucleus is made of protons and neutrons are made of quarks bound together by gluons. Now here is something that should genuinely shock you. The quarks inside a proton, the up quarks and down quarks that make up nearly all the visible matter in the universe, are extraordinarily light. An up quark has a mass of roughly 2.2 mega-electron volts. A down quark has a mass of roughly 4.7 mega-electron volts. A proton contains 2 up quarks and 1 down quark. If you add those quark masses together, you get about 9.1 mega-electron volts. But the actual mass of a proton is about 938.3 mega-electron volts. The quarks account for less than 2% of the proton's mass. Less than 2%. The rest, roughly 98% of the proton's mass, comes from somewhere else entirely. Not from the Higgs field, not from the quarks themselves. It comes from energy. This is one of the most remarkable facts in all of physics, and almost nobody knows about it. The mass of nearly everything you have ever touched, everything you see around you, every mountain, every ocean, every person, comes overwhelmingly not from the Higgs mechanism, but from the energy of the strong nuclear force binding quarks together inside protons and neutrons. To understand how this works, you need to understand something about the strong force. The strong nuclear force is carried by particles called gluons. Gluons are massless, like photons. But unlike photons, gluons interact with each other. Photons carry the electromagnetic force, but they do not carry electric charge themselves. So photons do not attract or repel other photons. Gluons are different. Gluons carry a type of charge called color charge, and because they carry this charge, they interact with each other. This makes the strong force behave in ways that are completely unlike electromagnetism. One of the most striking properties of the strong force is called confinement. Quarks are never found alone. You cannot isolate a single quark. You will never find one sitting by itself in a laboratory. Whenever quarks try to separate, the strong force between them gets stronger, not weaker. This is the opposite of how most forces work. Gravity gets weaker as objects move apart. Electromagnetism gets weaker as charges separate. But the strong force gets stronger as quarks try to pull away from each other. Imagine stretching a rubber band. The farther you pull, the harder the band pulls back. Eventually, if you pull hard enough, the rubber band snaps. But when the color force field between quarks snaps, something extraordinary happens. The energy stored in the stretched field is so large that it creates new quarks and antiquarks out of pure energy. Instead of freeing a quark, you create new particles. The quarks immediately bind with these new partners, forming new composite particles. You started trying to isolate a quark and ended up with more particles instead. The quarks remain confined, always bound, never free. Inside a proton, the three quarks are bound together in an incredibly dynamic environment. This is not a calm, orderly arrangement. The interior of a proton is a churning, roiling storm of activity. Gluons are constantly being exchanged between the quarks, flying back and forth, mediating the strong force. But because gluons interact with each other, they also create more gluons. And because the energy in these interactions is so high, quark-antiquark pairs are constantly popping into existence and disappearing. The interior of a proton is a seething quantum soup of quarks, antiquarks, and gluons, all interacting furiously. All of this activity involves energy, enormous amounts of energy relative to the tiny scale involved. The gluons carrying the force have energy. The quark-antiquark pairs flashing in and out of existence have energy. The kinetic energy of the quarks zipping around inside their confinement has energy. And energy, according to Einstein's most famous equation, E equals mc squared, is equivalent to mass. Energy and mass are two faces of the same coin. If you concentrate enough energy in a small region, that energy manifests as mass. This is not a metaphor. It is a precise physical law confirmed by countless experiments. This deserves a closer look, because the way this energy accumulates is stranger than it might sound. Consider the quarks first. They are confined to a space roughly 1 femtometer across, 1 quadrillionth of a meter. The uncertainty principle guarantees that being confined to such a tiny space means they must carry enormous momentum. They are not sitting still. They are moving at significant fractions of the speed of light within their confinement. Now consider the gluon field. It is one of the most intense force fields anywhere in nature. Unlike a gravitational or electromagnetic field that weakens smoothly with distance, the color force field between quarks stores more energy the farther you try to stretch it. The field is not a passive backdrop. It is a dynamic, energetic medium that contributes substantially to what you measure when you put a proton on a scale. And then there is a population of particles that most people never hear about. The energy inside the proton is so concentrated that pairs of quarks and antiquarks are constantly being created from the vacuum, existing for a fleeting moment and then annihilating. These are called C-quarks, as opposed to the 3 valence quarks that give the proton its identity as a proton rather than a neutron. At any given instant, the interior of a proton contains not just 3 quarks, but a churning population of gluons and C-quarks, all contributing to the total energy budget. Physicists have confirmed this picture through a remarkable computational technique called lattice QCD. The idea is conceptually straightforward, but computationally brutal. You take the equations of quantum chromodynamics and put them on a discrete grid, a lattice of points in 4-dimensional spacetime. Then you use supercomputers to calculate how quarks and gluons behave on this lattice, summing over all possible configurations of the gluon field and averaging the results. The calculation requires enormous computational resources. A single lattice QCD calculation of the proton mass can take millions of processor hours on the world's most powerful supercomputers. But the results are stunning. Starting from just a handful of inputs, the quark masses and the strong force coupling strength, lattice QCD reproduces the proton mass to within a few percent of the measured value. It confirms that the vast majority of the proton's mass emerges dynamically from QCD interactions, rather than from the intrinsic masses of the quarks. This is mass from nothing, or nearly nothing. You start with quarks that are almost massless, and a force carrier, the gluon, that is exactly massless. And the dynamics of their interaction generates a particle, the proton, that is 100 times heavier than its constituents combined. The mass materializes from energy, from motion, from the intensity of the force field. It is one of the most dramatic examples of emergence in all of physics. A property that does not exist in the individual components appears in the system as a whole. So when you weigh a proton, you are not primarily weighing the quarks inside it. You are weighing the energy of the strong force interactions holding those quarks together. The mass of a proton is almost entirely the energy of gluons and the kinetic energy of confined quarks, converted into mass through Einstein's equivalence. The quarks themselves, the matter particles whose masses come from the Higgs field, contribute almost nothing. This means that the Higgs mechanism, the celebrated achievement that won Nobel Prizes and made headlines around the world, is responsible for less than 2% of the mass of a proton. And since protons and neutrons make up the overwhelming majority of the mass of every atom, and atoms make up every object you interact with, this means the Higgs field is directly responsible for less than 2% of the mass of your body, less than 2% of the mass of Earth, less than 2% of the mass of the Sun. The rest comes from the strong force. From quantum chromodynamics, or QCD, the theory of the strong nuclear force. Let that sink in for a moment. The discovery that was celebrated as solving the mystery of mass actually explains only a tiny sliver of the mass you experience every day. The vast majority of the mass of visible matter has nothing to do with the Higgs field. It comes from the dynamics of the strong force, from gluons and quark confinement, and the seething quantum energy inside every proton and neutron in the universe. Now, you might be thinking that even if the Higgs only gives mass to a small fraction of total matter, at least it explains that fraction perfectly. At least for fundamental particles, the electrons and quarks and W and Z bosons, the Higgs mechanism provides a complete explanation. But it does not. And this is the second major gap in what the Higgs tells us about mass. As we discussed, the masses of fundamental particles are determined by their coupling strengths to the Higgs field, the Yukawa couplings. But these coupling strengths are free parameters. They are not predicted by anything. They are measured and inserted into the equations. The standard model does not explain why the electron couples to the Higgs field with one particular strength, while the muon couples with a strength 207 times greater. It does not explain why the tau lepton couples with a strength about 17 times greater still. It does not explain the pattern. Consider the leptons, the family of particles that includes the electron. There are 3 charged leptons. The electron, with a mass of about 0.511 megaelectronvolts, the muon, with a mass of about 105.7 megaelectronvolts, and the tau, with a mass of about 1,777 megaelectronvolts. 3 particles that appear to be identical in every way except for their mass. They have the same electric charge. They interact through the same forces. They obey the same quantum rules. The only difference is that each successive generation is heavier, much heavier. Why are there 3 generations? Why not 2, or 4, or 17? The standard model does not say. It accommodates 3 generations, but it does not require 3. You could write down a version of the standard model with 2 generations, or 4 generations, and the mathematics would work just fine. The existence of exactly 3 generations is an empirical fact without theoretical explanation. And the mass ratios between generations are bizarre. The muon is about 207 times heavier than the electron. The tau is about 17 times heavier than the muon. These are not round numbers. They are not powers of 2 or 10. They do not follow any obvious mathematical pattern. They look almost random, like someone chose them by throwing darts at a number line. To appreciate how strange this is, consider what a satisfying pattern might look like. If each generation were exactly 10 times heavier than the last, you would suspect a simple underlying rule. If the masses followed a known mathematical series, a power law, an exponential, a Fibonacci-like sequence, you would have a clue to work with. Physicists could start searching for a theory that produces that pattern. But the actual masses resist every simple description. People have tried fitting them to power laws, to exponentials, to formulas involving square roots and logarithms. Some fits look promising for a subset of particles, but fail when extended to the rest. Others require so many adjustable parameters that they explain nothing. You end up with a formula as complicated as the data it was supposed to simplify. This is not for lack of effort. Since the 1970s, hundreds of papers have been written proposing mass formulas and texture models for the Yukawa coupling matrices. Some invoke discrete symmetries, proposing that the three generations transform into each other under specific mathematical operations, and that the symmetry-breaking pattern determines the mass ratios. Others invoke continuous symmetries, or extra dimensions, or radiative corrections, where lighter generations get their masses through quantum loop effects rather than direct coupling. These models are creative and mathematically interesting, but none has emerged as clearly correct. None has made a prediction that was subsequently confirmed. The flavor puzzle remains stubbornly unsolved. What makes this even more frustrating is that the standard model does not even tell you how many generations there should be. 3 is an experimental fact. Precision measurements of the Z boson's decay width at the LEP collider at CERN in the early 1990s showed that there are exactly 3 generations of light neutrinos. If there were a 4th generation with a light neutrino, the Z boson would decay slightly faster, and the measurements ruled this out conclusively. So we know there are 3 generations, but the standard model would work perfectly well with 2 or 4 or 20. The number 3 is not derived from any principle within the theory, it is simply observed. So the Higgs mechanism gives mass to fundamental particles, but it offers no insight into the pattern of those masses, the number of generations, or the mixing between them. The mechanism is the plumbing. The specific flow rates through each pipe are a complete mystery. The situation is even worse for quarks. There are 6 quarks, arranged in 3 generations, just like the leptons. The up quark has a mass of roughly 2.2 mega-electron volts. The down quark, about 4.7 mega-electron volts. The charm quark, about 1,275 mega-electron volts. The strange quark, about 95 mega-electron volts. The top quark, about 173,000 mega-electron volts. The bottom quark, about 4,180 mega-electron volts. These masses span 5 orders of magnitude. The top quark is roughly 80,000 times heavier than the up quark. There is no explanation for this hierarchy. No known principle that determines these values. No pattern that anyone has been able to identify, despite decades of trying. Some of the greatest minds in theoretical physics have spent entire careers searching for a formula, a symmetry, a principle, anything that would predict these masses from some deeper theory. So far, nothing has worked. This collection of unexplained numbers is sometimes called the flavor puzzle. Flavor is the term physicists use to distinguish between different types of quarks and leptons. The electron, muon, and tau are different flavors of charged lepton. The up, down, charm, strange, top, and bottom quarks are different flavors of quark. The flavor puzzle is the question of why these flavors exist, why there are exactly 3 generations, and why the masses follow the particular pattern they do. The Higgs mechanism provides the stage on which these masses appear, but it does not write the script. That deeper rule remains unknown. And then there is the deepest mass mystery of all in the standard model: neutrinos. For decades, the standard model treated neutrinos as massless particles. This was not an approximation or a simplification. It was built into the structure of the theory. The original standard model contained no mechanism for giving neutrinos mass. This seemed fine for a long time because neutrinos are incredibly difficult to detect. They interact so weakly with matter that trillions of them pass through your body every second without disturbing a single atom. Measuring their properties is extraordinarily challenging. But in the late 1990s and early 2000s, experiments delivered a surprise that shook particle physics to its core. Neutrinos have mass. They are not massless. This was demonstrated through a phenomenon called neutrino oscillation, and understanding it requires a brief detour into one of quantum mechanics' stranger features. There are 3 types, or flavors, of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Each is associated with its corresponding charged lepton. When a nuclear reaction in the Sun produces a neutrino, it produces an electron neutrino specifically. When a muon decays, it produces a muon neutrino. The flavors are distinct. But quantum mechanics allows something peculiar. If neutrinos have mass, and if the mass states do not line up perfectly with the flavor states, then a neutrino created as one flavor can transform into another flavor as it travels. An electron neutrino produced in the Sun can arrive at Earth as a muon neutrino or a tau neutrino. It oscillates between flavors during its journey, shifting identity as it flies through space. The key point is that this oscillation can only happen if neutrinos have mass. If they were truly massless, they could not oscillate. The math forbids it. Oscillation requires different mass states, and different mass states require non-zero mass. So the observation of neutrino oscillation is direct proof that neutrinos have mass. The experimental evidence came from several directions. The Super Kamiokande experiment in Japan, a massive underground detector filled with 50,000 tons of ultra-pure water, observed atmospheric neutrinos oscillating between flavors. The Sudbury Neutrino Observatory, known as SNO in Canada, solved the long-standing solar neutrino problem by showing that electron neutrinos from the Sun were converting to other flavors during their journey to Earth. The total number of neutrinos arriving matched predictions perfectly. They were not disappearing, they were changing flavor. These discoveries earned Takaaki Kajita and Arthur MacDonald the Nobel Prize in Physics in 2015. Their work proved beyond any doubt that neutrinos have mass. And this was a problem for the Standard Model, because the Standard Model, as originally constructed, had no way to give neutrinos mass. To understand why, you need to know something about how particles come in different varieties based on a property called chirality, which is related to how a particle's spin aligns with its direction of motion. In the Standard Model, the Yukawa coupling that gives a fermion its mass works by connecting the left-handed version of the particle to the right-handed version through the Higgs field. Both versions must exist for the coupling to work. For the electron, this is fine. Left-handed electrons and right-handed electrons both exist and interact in the Standard Model. The Higgs field connects them, and the electron gets its mass. But the original Standard Model contained only left-handed neutrinos. There were no right-handed neutrinos in the theory. Without a right-handed neutrino, there is nothing for the Higgs field to connect the left-handed neutrino to. The standard Yukawa coupling mechanism simply cannot work. So how do neutrinos get mass? This is one of the biggest open questions in particle physics, and there is no confirmed answer. Several possibilities exist, and each points to physics beyond the Standard Model. One possibility is that right-handed neutrinos do exist, but are extremely heavy and have not yet been detected. These heavy right-handed neutrinos could interact with the Higgs field in the usual way, but their extreme mass would make the resulting neutrino masses tiny through a clever mechanism called the seesaw mechanism. The idea is elegant. If the right-handed neutrino has an enormous mass, the mathematics of mixing between left-handed and right-handed states produces an extremely light neutrino. The heavier the right-handed partner, the lighter the observed neutrino. It is like a seesaw. Push one end up, the other goes down. This would naturally explain why neutrino masses are so incredibly small compared to all other particle masses. But it requires the existence of particles we have never observed, right-handed neutrinos with masses potentially far beyond the reach of any existing accelerator. Another possibility involves a different type of mass term altogether. Ordinary particles, like electrons, are called Dirac fermions. They have distinct particle and antiparticle versions. But there is another theoretical possibility. A particle could be its own antiparticle. Such particles are called Majorana fermions, named after the Italian physicist Ettore Majorana, who proposed the concept in 1937. If neutrinos are Majorana fermions, they could acquire mass through a different mechanism that does not require the standard Yukawa coupling at all. This would be a fundamentally new type of mass, generated through physics we do not yet understand. Experiments around the world are searching for evidence that would distinguish between these possibilities. One key test is the search for a hypothetical process called neutrinoless double beta decay. In ordinary double beta decay, 2 neutrons in a nucleus simultaneously decay into protons, emitting 2 electrons and 2 antineutrinos. This has been observed. But if neutrinos are their own antiparticles, a rarer process could occur where the 2 antineutrinos annihilate each other inside the nucleus. The result would be double beta decay with no neutrinos emitted at all, only 2 electrons carrying away all the energy. Detecting this process would prove neutrinos are Majorana fermions and would reveal something fundamentally new about the nature of mass. So far, no experiment has observed neutrinoless double beta decay, but the search continues with ever more sensitive detectors. The implications of a discovery would be enormous. It would prove the existence of a mass-generating mechanism completely separate from the Higgs field. It would demonstrate that the standard model is incomplete in a very specific, measurable way. And there is yet another strange fact about neutrino masses. We do not actually know what those masses are. Oscillation experiments tell us the differences between the squared masses of the 3 neutrino types, but not the absolute masses themselves. We know the differences are tiny, corresponding to mass splittings on the order of thousandths to hundredths of an electron volt. This makes neutrinos at least 1,000,000 times lighter than the electron, the next lightest particle. Whatever mechanism gives neutrinos their mass must explain why that mass is so absurdly small compared to every other massive particle in the standard model. The mass of neutrinos is not just a detail, it is a clue. It is a signpost pointing toward physics beyond the standard model. The standard model cannot accommodate neutrino masses in its original form. Any explanation requires new particles, new interactions, or new principles. Neutrino mass is proof that the standard model, for all its triumphs, is incomplete. And the way in which it is incomplete might tell us something deep about the nature of mass itself. Let me now step back and put all of this together, because the picture that emerges is striking. When people heard that the Higgs boson was discovered, the natural interpretation was that the mystery of mass had been solved. The headlines certainly encouraged that view, but the reality is far more nuanced and far more interesting. The Higgs mechanism explains how certain fundamental particles acquire mass. It explains the process. A particle interacts with the Higgs field, and that interaction gives it mass. This is real, confirmed, important. Without the Higgs mechanism, the W and Z bosons would be massless, and the weak force would behave completely differently. The universe as we know it could not exist without the Higgs field. But the Higgs mechanism does not explain why each particle has the specific mass it has. The coupling strengths are free parameters, unexplained numbers plugged in by hand. The pattern of masses across generations, spanning 12 or more orders of magnitude, from the lightest neutrinos to the heaviest top quark, remains completely mysterious. And the Higgs mechanism does not explain the mass of composite particles like protons and neutrons, which make up the overwhelming majority of the mass of visible matter. Proton mass comes almost entirely from the energy of the strong force, from QCD dynamics, from gluons and quark confinement. This is a completely different mechanism from the Higgs, governed by a completely different force, operating through completely different physics. And the Higgs mechanism cannot even explain neutrino masses, which require new physics beyond the standard model to account for. So the word mass, which sounds like it should refer to one single phenomenon, actually refers to at least 3 distinct things. There is the mass that fundamental particles get from the Higgs field. There is the mass that composite particles get from the binding energy of the strong force. And there is the mass that neutrinos have through some still unknown mechanism. These are not the same phenomenon. They are different phenomena that happen to produce the same observable property: a resistance to acceleration, a gravitational pull. The Higgs boson was a triumph. Its discovery confirmed a beautiful and essential piece of the standard model. But it did not solve the problem of mass. It solved one layer of the problem, the question of how certain particles can have mass at all without destroying the mathematical consistency of the theory. The deeper layers, why those masses have the values they do, why composite matter gets its mass from a completely different source, and how neutrinos fit into the picture, remain as mysterious as ever. And as we are about to discover, the problems go deeper still. Because the Higgs boson itself, the particle that was supposed to complete the standard model, raises profound questions about its own existence, its mass, its properties, the very structure of the Higgs sector. All of these point to puzzles that the Standard Model cannot resolve. The Higgs boson did not just confirm a theory, it opened a door to problems that may require entirely new physics to solve. The Higgs mechanism explains how certain fundamental particles acquire mass, but not why those masses have the particular values they do. Most of the mass in ordinary matter comes not from the Higgs field at all, but from the energy of the strong force binding quarks inside protons and neutrons. And neutrino masses remain unexplained, requiring physics beyond the Standard Model. These are serious gaps. But there is another problem, and in many ways it is the most disturbing one of all. It concerns the Higgs boson itself. These are serious gaps, but there is another problem, and in many ways it is the most disturbing one of all. It concerns the Higgs boson itself. The Higgs boson was discovered with a mass of approximately 125 giga-electron volts. That number was measured at the Large Hadron Collider by 2 independent experiments, confirmed and refined over subsequent years of data collection. It is one of the most precisely known quantities in particle physics. But here is the problem. According to the Standard Model's own mathematics, that mass should not be 125 giga-electron volts. It should be enormously, catastrophically, absurdly larger. And the fact that it is not requires either an explanation we do not have, or a coincidence so extreme it borders on the unbelievable. To understand why, you need to understand something about how quantum mechanics affects the properties of particles. In quantum field theory, nothing exists in isolation. Every particle interacts with every other particle and with the quantum vacuum itself. Even in what we think of as empty space, quantum fields are constantly fluctuating. Virtual particles pop into and out of existence, borrowing energy from the vacuum for brief moments before vanishing. These are not hypothetical. Their effects have been measured with extraordinary precision. They are as real as the particles you can detect in a laboratory. These quantum fluctuations affect the properties of all particles, including the Higgs boson. Specifically, they affect the Higgs boson's mass. In quantum field theory, the mass of a particle is not simply a fixed number written into the equations. It receives contributions from all the virtual particles that interact with it. Every particle that couples to the Higgs field contributes a correction to the Higgs boson's mass. The top quark contributes. The W and Z bosons contribute. Every particle in the Standard Model that interacts with the Higgs field sends its own quantum correction. For most particles, these corrections are small and manageable. They shift a particle's mass slightly, and the shift can be calculated and accounted for. But the Higgs boson is different. The Higgs boson is a scalar particle, a particle with zero spin. This is important because the way quantum corrections work for scalar particles is fundamentally different from how they work for particles with spin. For particles with spin, like electrons or W bosons, certain symmetries protect their masses from receiving enormous quantum corrections. These symmetries ensure that the corrections are proportional to the particle's own mass. So if the particle starts with a small mass, the corrections remain small. Scalar particles have no such protection. Nothing in the known laws of physics prevents a scalar particle's mass from receiving quantum corrections that are enormous, corrections that are proportional not to the particle's own mass, but to the highest energy scale in the theory. And in the Standard Model, the highest energy scale is the Planck scale, the scale at which gravity becomes as strong as the other forces and quantum gravitational effects become important. The Planck scale corresponds to an energy of roughly 10 to the 18 giga-electron volts. That is an incomprehensibly large number. It is about 10,000 trillion times the energy at which the Higgs boson was discovered. When you calculate the quantum corrections to the Higgs boson's mass in the Standard Model, including contributions from all virtual particles up to the Planck scale, the result is staggering. The corrections are not small, they are not modest. They push the Higgs mass up toward the Planck scale itself. The natural expectation, the value you would calculate if you just let the mathematics run without any fine-tuning, is a Higgs boson mass of roughly 10 to the 18 giga-electron volts. That is not 125 giga-electron volts. It is not even in the same universe of numbers. It is 10 to the 16 times larger than the observed value. 16 orders of magnitude. The predicted mass and the observed mass differ by a factor of 10,000 trillion. This is the hierarchy problem. It is one of the most famous and most troubling puzzles in all of theoretical physics. The question it asks is simple. Why is the Higgs boson so light? Now, you might think there is an obvious answer. Maybe the quantum corrections just happen to cancel. Maybe the contributions from different virtual particles push in opposite directions, some making the mass larger and some making it smaller, and they nearly cancel, leaving the small observed value. And in fact, this is technically what must happen in the standard model. The bare mass of the Higgs boson, the number written in the fundamental equations before quantum corrections, must be chosen with extraordinary precision, so that when you add all the enormous quantum corrections, the result is exactly 125 giga-electron volts. The bare mass must cancel against the quantum corrections to better than 1 part in 10 to the 32. Let me say that again. The cancellation must be precise to 1 part in 10 to the 32. That is 1 part in 100 million trillion trillion. Imagine you had to subtract two numbers, each with 34 digits, and the result had to be a specific 3-digit number. If any single digit in either number was off by 1, the result would be completely wrong. The calculation would not give 125. It would give some enormous number near the Planck scale, and the universe would look nothing like what we observe. This kind of cancellation is what physicists call fine-tuning. And fine-tuning makes physicists deeply uncomfortable. Not because it is mathematically impossible, it is perfectly possible, the equations allow it, but because it seems to require an incredible coincidence with no explanation. It is like balancing a pencil on its point. It is technically possible. The laws of physics allow a pencil to stand perfectly upright on its tip. But you would never expect to walk into a room and find a pencil balanced that way by accident. If you did find one, you would look for a mechanism. Someone put it there. Something is holding it up. There must be an explanation. This expectation that the parameters of a fundamental theory should not require implausible fine-tuning is called naturalness. It is not a rigorous mathematical principle. It is more of a guiding philosophy, a heuristic that has served physics well for decades. When a theory requires fine-tuning, it usually means there is a deeper explanation waiting to be found. Some hidden mechanism, some unrecognized symmetry, something that makes the apparently miraculous cancellation natural rather than accidental. The concept of naturalness was articulated most clearly by the Dutch physicist Gerard 't Hooft in the late 1970s. He proposed that a parameter in a physical theory is natural if setting it to 0 would increase the symmetry of the theory. This is why the electron's mass is natural. If the electron were massless, the theory would have an additional symmetry called chiral symmetry. This symmetry protects the electron mass from large quantum corrections. The corrections are always proportional to the electron mass itself, so if the mass starts small, the corrections remain small. There is a reason the electron mass is small. The symmetry ensures it. But the Higgs boson has no such protection. No known symmetry in the standard model prevents the Higgs mass from receiving enormous corrections. Setting the Higgs mass to 0 does not increase the symmetry of the theory in any known way. There is no mechanism within the standard model that makes a small Higgs mass natural. The smallness of the Higgs mass, relative to the Planck scale, appears to be a brute fact, an incredibly precise coincidence with no explanation. Let me try to make the hierarchy problem more vivid, because its severity is easy to understate. Imagine you are calculating the balance in a bank account. The account receives deposits and withdrawals from many different sources. Some deposits are enormous, billions of dollars. Some withdrawals are equally enormous, also billions of dollars. Each individual transaction is huge, but when you add them all up, the final balance must be exactly $125.37. Not $125.38, not $125.36, exactly $125.37. If any single transaction among those billions were different by even a tiny amount, the balance would be completely wrong. It would be billions of dollars instead of 125. That is what the hierarchy problem looks like in practice. The quantum corrections to the Higgs mass are like those enormous deposits and withdrawals. Each one is colossal, proportional to the square of the highest energy scale in the theory. They push the mass up and down by amounts that are 10 to the 16 times larger than the final answer, and yet they must cancel with extraordinary precision to leave the observed value. Each contribution is enormous. The sum must be tiny, and there is no mechanism within the standard model that enforces this cancellation. It just has to happen, digit by digit, for 32 decimal places. This is not like other fine-tuning problems in physics. The cosmological constant, the energy density of empty space, has an even worse fine-tuning problem. But the hierarchy problem is special because it directly concerns the Higgs boson, the particle that was supposed to complete the standard model. The very object that was celebrated as the final piece of the puzzle turns out to raise the most severe naturalness problem in the theory. Its mass is the number that makes the least sense. Physicists sometimes describe this by saying the Higgs mass is ultraviolet sensitive. Ultraviolet here does not mean the kind of light that gives you sunburn. It is physics jargon for high energy or short distance. The Higgs mass is sensitive to whatever physics exists at the highest energy scales, even if those scales are far beyond what we can probe. Whatever happens at the Planck scale, at the grand unification scale, at any high energy scale, it feeds directly into the Higgs mass. The Higgs boson is like an antenna that picks up signals from every energy scale in the universe and sums them all into its mass. For that sum to give 125 giga-electron volts requires either a profound explanation or a staggering accident. This troubled physicists enormously, and for decades before the Higgs boson was discovered, they proposed solutions. The most popular and most developed solution was supersymmetry, often abbreviated as SU-Z. Supersymmetry proposes that every known particle has a heavier partner particle with different spin properties. For every fermion, a particle with half-integer spin like quarks and electrons, there would be a partner boson with integer spin. For every boson, there would be a partner fermion. The electron would have a partner called the selectron. The quarks would have partners called squarks. The photon would have a partner called the photino. The Higgs boson would have a partner called the Higgsino. The beauty of supersymmetry is that it solves the hierarchy problem naturally. The quantum corrections to the Higgs mass from ordinary particles would be exactly cancelled by the corrections from their supersymmetric partners. The contributions from fermions push the mass in one direction. The contributions from their partner bosons push it in exactly the opposite direction. The cancellation is not an accident. It is guaranteed by the symmetry. Just as chiral symmetry protects the electron mass, supersymmetry would protect the Higgs mass. The enormous quantum corrections would cancel automatically, leaving a small Higgs mass without any fine-tuning. This was enormously appealing. Supersymmetry was elegant. It was mathematically consistent. It solved the hierarchy problem. It also had other attractive features. It provided a natural candidate for dark matter, the mysterious substance that makes up about 27% of the universe's total energy content. The lightest supersymmetric particle, if stable, would have exactly the right properties to be dark matter. Supersymmetry also improved the unification of forces. In the standard model, the strengths of the three forces approach each other at high energies, but do not quite meet. With supersymmetry, they converge precisely at a single point, suggesting a deeper unification. For all these reasons, supersymmetry was the dominant paradigm in theoretical particle physics for decades. Thousands of papers were written about it. Entire careers were built on it. When the Large Hadron Collider was being designed and constructed, one of its primary goals was to discover supersymmetric particles. Many physicists were confident that supersymmetry would be found. Some considered it almost inevitable. It was not found. The LHC has been running since 2010. Two massive detectors, ATLAS and CMS, have analysed trillions of proton collisions at the highest energies ever achieved in a laboratory. They have searched for supersymmetric particles in every way imaginable. They have looked for squarks and gluinos, for leptons and charginos, for neutralinos and stop quarks. They have searched in dozens of different channels, using hundreds of different analysis techniques, examining datasets of unprecedented size and quality. They have found nothing. No supersymmetric particles. No sign of any partner particles. no hint of supersymmetry in any form. The data is consistent with the standard model and nothing else. Every search has come back empty. The limits on supersymmetric particle masses have been pushed higher and higher. If supersymmetric partners exist, they must be heavier than about 2,000 giga-electron volts for many particle types, and even heavier for others. And if they are that heavy, they no longer solve the hierarchy problem cleanly. The whole point of supersymmetry was to cancel the quantum corrections to the Higgs mass. If the supersymmetric partners are very heavy, the cancellation is no longer exact. You still need some fine-tuning, perhaps not as extreme as without supersymmetry, but still uncomfortable. The emotional impact of this absence on the physics community is difficult to overstate. For decades, supersymmetry had been more than a hypothesis. It had become a framework, almost a worldview. Graduate students were trained in it. Textbooks were written about it. Conferences were organized around it. Careers were built on calculating its predictions. When the LHC began operating, there was a palpable sense of anticipation. Many physicists expected to discover supersymmetric particles within the first few years of data. Some had made public predictions, confident that the partners would appear at energies just above what previous colliders could reach. Instead, the data came back clean. No excess events, no unexpected bumps in the mass distributions, no missing energy signatures that could not be accounted for by known processes. Just the standard model, working perfectly, with nothing extra. Year after year, run after run, the results were the same. The limits on supersymmetric particle masses crept upward. The parameter space shrank. The most natural versions of supersymmetry, the ones that solve the hierarchy problem most elegantly, with partner particles light enough to be produced easily, were ruled out one by one. This forced a reckoning. Some physicists remained committed to supersymmetry, arguing that the partners might simply be heavier than expected, lurking just beyond the current reach. Others began to question whether naturalness itself was a reliable guide. Perhaps the universe is fine-tuned, and our discomfort with that idea reflects human bias rather than physical truth. Still others turned to alternative approaches that had long lived in the shadow of supersymmetry. Among these alternatives, composite Higgs models gained renewed attention. In these models, the Higgs boson is not an elementary particle, but a bound state of new, strongly interacting particles, analogous to how pions are bound states of quarks. The compositeness scale would cut off the dangerous quantum corrections, softening the hierarchy problem without requiring supersymmetric partners. Other approaches, such as real-action models, propose that the Higgs mass was set dynamically in the early universe through a cosmological evolution process, the Higgs mass scanning across many values until it settled at a small value through a specific stopping mechanism. These ideas are creative and theoretically motivated, but none has yet produced a confirmed experimental signature. This is one of the most significant experimental results in recent particle physics history, and it is a negative result. The absence of supersymmetry at the LHC has left theoretical physics in a difficult position. The most popular, most developed, most motivated solution to the hierarchy problem has not shown up where it was expected. Other proposed solutions, such as extra dimensions of space or composite Higgs models, where the Higgs boson is not fundamental but made of smaller constituents, have also been searched for and not found. This leaves physicists with a genuine puzzle. The hierarchy problem has not gone away. The Higgs mass is still 125 giga-electron volts. The quantum corrections are still enormous. The fine-tuning is still 1 part in 10 to the 34, or whatever the exact number turns out to be, depending on where you place the cutoff scale. Something must be going on. Either there is a mechanism we have not yet discovered, or the naturalness principle is wrong, or there is something about the hierarchy problem we do not yet understand. Some physicists have begun to question whether naturalness is a reliable guide at all. Perhaps fine-tuning is not as implausible as it seems. Perhaps the parameters of the universe simply are what they are, and there is no deeper explanation. Perhaps what looks like a miraculous cancellation is just how the universe works, and our expectation that it should be otherwise reflects our human intuition rather than any physical principle. This is a minority view, but it has gained some traction as experiment after experiment fails to find new physics beyond the standard model. Other physicists have turned to a more radical possibility. Maybe the fine-tuning is real, but it is explained not by a mechanism, but by selection. This is the anthropic argument. The idea is that the Higgs mass might vary across different regions of a larger multiverse, taking different values in different domains. In most domains, the Higgs mass would be near the Planck scale, and the universe would look nothing like ours. Atoms would not form, stars would not ignite, life would be impossible. Only in the rare domains where the Higgs mass happens to be small, where the fine-tuning happens to work out, would observers like us exist to ask the question. We observe a small Higgs mass, not because any mechanism forced it to be small, but because we could only exist in a region where it is small. This idea is deeply controversial. Critics argue that it is not really science, because it does not make testable predictions in any straightforward way. Proponents argue that it might be the correct explanation whether we like it or not, especially if the landscape of string theory provides the necessary multiverse of possibilities. The debate is far from settled, and it touches on fundamental questions about what counts as a scientific explanation. Beyond the hierarchy problem, the Higgs sector raises other troubling questions. The shape of the Higgs potential, the energy landscape that determines the Higgs field's behavior, has a very specific form. It must have the right shape to ensure that the Higgs field settles into a non-zero value, breaking the electroweak symmetry. That shape is determined by a handful of parameters, and those parameters must take specific values for the universe to work the way it does. Too different, and the Higgs field might not break the symmetry at all, leaving all particles massless. Or it might break it too strongly, giving particles vastly different masses than what we observe. And here is something even more unsettling. Precision measurements of the Higgs boson's mass and the top quark's mass suggest that the Higgs potential might not be absolutely stable. The universe might be sitting in what physicists call a metastable vacuum. To understand what this means, imagine a ball resting in a shallow valley halfway up a hillside. The ball is stable in the sense that small pushes will not dislodge it. It will roll back and forth and settle back into the valley. But it is not in the lowest point on the entire landscape. There is a deeper valley farther down the hillside. If the ball received a large enough push, it could roll over the ridge and tumble down into the deeper valley, never to return. Current measurements suggest the universe might be in this situation. The Higgs field sits at a particular value, in a particular valley of its potential. But there might be a deeper valley at much higher field values, a more stable configuration that the universe has not yet reached. If this is the case, the universe is metastable. It is stable enough to have lasted 13.8 billion years so far, and calculations suggest it would remain stable for an unimaginably long time, far longer than the current age of the universe. So there is no immediate danger, but in principle, through quantum tunneling, a bubble of the deeper vacuum could spontaneously nucleate somewhere in the universe. Inside this bubble, the Higgs field would have a different value, and the laws of physics would be different. The bubble would expand at nearly the speed of light, converting everything it touched into the new vacuum state. Everything inside the bubble, matter, energy, the structures we know, would be transformed beyond recognition. You would never see it coming, because the bubble wall approaches at the speed of light. No warning is possible. This scenario is speculative and depends on details of physics at extremely high energies that we cannot currently measure. The conclusion that the vacuum is metastable depends on the precise values of the Higgs boson mass and the top quark mass, and small shifts in these values could change the conclusion. If there is new physics at higher energies, new particles or new interactions we have not yet discovered, they could stabilize the vacuum completely. Many physicists expect that some form of new physics exists at higher energies, precisely because a metastable vacuum seems unsatisfying as a final state of affairs. But notice what this means. The Higgs sector, the part of the standard model that was supposed to explain mass, might itself be unstable. The very mechanism that gives particles mass and makes the universe possible might be a temporary arrangement, a local minimum rather than the true ground state of nature. The universe might be living on borrowed time, in a sense, existing in a configuration that is not the most stable one available. This is not the picture of a completed, closed story. It is the picture of a theory that raises as many questions as it answers. There is another dimension to the puzzle of the Higgs sector. In the Standard Model, there is exactly one Higgs field and one Higgs boson, but there is no deep reason why this should be the case. The mathematics allows for more. Many extensions of the Standard Model propose additional Higgs fields and additional Higgs bosons. Supersymmetry, for instance, requires at least 2 Higgs fields, producing a total of 5 Higgs bosons. Other models have even more. If additional Higgs bosons exist, they would have different masses and different properties from the one already discovered. They might be heavier, perhaps much heavier, which is why they have not been found yet. Or they might couple differently to known particles, making them harder to produce or harder to detect. The LHC is actively searching for additional Higgs bosons. So far, none have been found. But the searches continue, and future colliders with higher energies would extend the reach significantly. The existence of additional Higgs bosons would change the picture dramatically. It would mean the Higgs sector is richer and more complex than the minimal version in the Standard Model. It would provide new parameters, new couplings, new sources of symmetry breaking. It could potentially explain some of the puzzles we have discussed, such as the pattern of fermion masses, or at least provide new clues. But it would also raise new questions. Why those particular additional Higgs bosons? Why those particular masses and couplings? Unless a deeper principle determines the structure of the Higgs sector, adding more Higgs bosons just replaces one set of unexplained parameters with a larger set. And then there is the question of what the Higgs field really is. In the Standard Model, it is treated as a fundamental field, as fundamental as the electron field or the quark field. But some physicists have proposed that the Higgs boson might not be fundamental at all. It might be a composite object, made of more basic constituents bound together by a new force, much as protons are made of quarks bound by the strong force. If the Higgs boson is composite, its internal structure would become apparent at higher energies. The Higgs boson would not be a point particle, but an extended object with a finite size. At low energies, it would look fundamental, just as protons look fundamental at energies too low to resolve their internal quark structure. But at higher energies, the composite nature would reveal itself. Composite Higgs models have been proposed and studied for decades. They are theoretically motivated because a composite Higgs could solve the hierarchy problem. If the Higgs boson is not fundamental, the quantum corrections to its mass are cut off at the scale of its internal structure, rather than at the Planck scale. The hierarchy problem is softened because the relevant energy scale is the compositeness scale, which could be much lower than the Planck scale. The LHC has searched for signs that the Higgs boson is composite, looking for deviations from Standard Model predictions in how the Higgs is produced and how it decays. So far, the Higgs boson behaves exactly like a fundamental scalar, precisely as the Standard Model predicts. No signs of compositeness have been found, but the measurements are not yet precise enough to rule out all composite models. Future experiments, with more data and higher precision, will continue to test this possibility. The situation with the Higgs sector is therefore profoundly open. We have discovered the Higgs boson, we have measured its mass, we have confirmed that it behaves like the Standard Model predicts, at least to the precision of current experiments. But the Standard Model itself tells us that the Higgs mass is unnatural. It requires fine-tuning that has no explanation. The most popular theoretical solution, supersymmetry, has not appeared at the energies we have probed. The Higgs potential might place the universe in a metastable state. The Higgs sector might be more complex than the minimal version we know, with additional particles waiting to be discovered. And the Higgs boson itself might not be fundamental. Every one of these possibilities points to something beyond the Standard Model, something we have not yet found, something that would explain why the Higgs sector looks the way it does. The discovery of the Higgs boson did not close the book on mass. It opened a new chapter, one filled with questions that the Standard Model cannot answer. The hierarchy problem is not an abstract theoretical curiosity. It is a concrete, quantitative statement about the relationship between the Higgs mass and the Planck scale. It says that either there is a mechanism we have not discovered, or there is a coincidence we cannot explain, or our understanding of quantum field theory is incomplete in some fundamental way. Any of these possibilities would be revolutionary. and none of them has been confirmed or ruled out. What physicists are left with, after the discovery of the Higgs boson and the absence of new particles at the LHC, is a theory that works spectacularly well at describing what we can measure, but raises deep questions about its own structure. The Standard Model is like a map that accurately guides you through a city, but has blank regions marked with warnings that the territory beyond is unknown. The Higgs sector is one of those blank regions. We know it exists. We know some of its features, but we do not understand why it has those features, and our best attempts to explain them have so far come up empty. This is not a failure. This is what progress looks like when you reach the frontier of knowledge. The Higgs boson was found precisely where the theory said it should be. Every measurement of its properties has confirmed the Standard Model's predictions. This means the theory is right about what the Higgs sector does. The question is whether the theory is right about what the Higgs sector is. And on that question, the answer is almost certainly no. The Standard Model is almost certainly not the final word. Something deeper is waiting to be found. The hierarchy problem, the naturalness puzzle, the metastability of the vacuum, and the unexplained structure of the Higgs potential are all signposts pointing in the same direction. They all say the same thing. The Higgs sector, as we currently understand it, is incomplete. There is more to the story. And whatever that more turns out to be, it will change our understanding of mass, of particles, and of the fundamental structure of the universe. So what does the full landscape of mass actually look like in modern physics? Because one of the most surprising things we have uncovered on this journey is that mass is not a single phenomenon. It is not one thing with one explanation. It is several different phenomena, generated by different mechanisms, operating at different scales, governed by different physics. And no single theory explains all of them. Start with the first layer. Fundamental particles, the quarks, the electrons, the muons, the taus, the W and Z bosons, acquire their masses through their interaction with the Higgs field. This is the Higgs mechanism. It is real, it is confirmed. It works through spontaneous symmetry breaking, where the Higgs field settles into a non-zero value throughout the universe and gives mass to particles that interact with it. The stronger the interaction, the greater the mass. The Higgs boson, discovered in 2012, is the excitation of this field, the proof that the field exists. This layer of mass generation is well understood in terms of how it operates, but completely unexplained in terms of why it produces the specific values it does. The coupling strengths are free parameters. They are measured, not derived. Nobody knows why the electron couples to the Higgs field with a strength that gives it a mass of 0.511 megaelectron volts, or why the top quark couples with a strength that gives it a mass roughly 340,000 times larger. Now consider the second layer. Composite particles, protons and neutrons, get the overwhelming majority of their mass not from the Higgs field, but from the energy of the strong nuclear force. Quarks inside a proton are bound together by gluons. The dynamics of that binding, the constant exchange of gluons, the creation and annihilation of quark-antiquark pairs, the kinetic energy of confined quarks, all of this generates enormous energy relative to the tiny scale of the proton. That energy is equivalent to mass through Einstein's relation E equals mc squared. Roughly 98% of a proton's mass comes from this mechanism. This means roughly 98% of the mass of every atom, every molecule, every object you have ever touched comes from QCD binding energy rather than from the Higgs field. This second layer is, in a sense, better understood than the first. The theory of the strong force, quantum chromodynamics, is a well-defined mathematical framework. Given the quark masses as inputs, the proton mass can be calculated from the equations of the strong force alone, and as we saw earlier, those calculations succeed remarkably well. The mechanism by which protons get their mass is understood. It emerges from QCD dynamics. But notice the catch. The calculation requires the quark masses as inputs, and those quark masses come from the Higgs mechanism, which does not explain them. The second layer depends on the first, and the first is unexplained. Then there is the third layer, neutrino masses. These tiny masses, confirmed by oscillation experiments, cannot be generated by the standard Higgs mechanism in its original form. The standard model, as originally constructed, predicted neutrinos to be massless. The fact that they are not is direct evidence of physics beyond the standard model. Whatever mechanism gives neutrinos their mass, whether it involves right-handed neutrinos and the seesaw mechanism, Majorana mass terms, or something else entirely, it is a genuinely new piece of physics that we have not yet identified. So mass is not one mystery, it is at least three mysteries layered on top of each other, and they are connected. The quark masses that enter the QCD calculation come from the Higgs field. The Higgs field's non-zero value is determined by the Higgs potential, whose shape is unexplained. The Higgs boson's own mass raises the hierarchy problem, and neutrino masses point to physics beyond everything we currently know. Pull on any thread, and you find it connected to all the others. Now consider what all of these unexplained masses look like when you put them together. The standard model has roughly 26 free parameters. These are numbers that the theory does not predict. They must be measured and inserted by hand. Among these parameters are the masses of the 6 quarks, the masses of the 3 charged leptons, the mass of the Higgs boson, and the parameters describing neutrino masses and mixing. There are also the coupling strengths of the 3 forces, mixing angles that describe how quarks transform into one another through the weak force, and a few other parameters. The vast majority of the standard model's free parameters are directly related to mass and the Higgs sector. This is extraordinary. We have a theory that is spectacularly successful at describing the behavior of fundamental particles, a theory that has been tested to extraordinary precision and has never been contradicted by any experiment. And yet, more than half of its inputs are just numbers we measure without understanding where they come from. The standard model is like a recipe that produces a perfect meal every time, but includes a list of ingredients whose quantities are marked with question marks. The recipe works, the meal is delicious, but nobody knows why those particular quantities produce that particular result. The mixing angles deserve a brief mention because they deepen the puzzle. When quarks interact through the weak force, they can change flavor. An up quark can become a down quark, or a charm quark, or a strange quark. The probabilities of these transitions are described by a mathematical object called the CKM matrix, named after Nicola Kabibo, Makoto Kobayashi, and Toshihide Masukawa. This matrix contains 4 independent parameters, 3 mixing angles, and 1 phase. These parameters are related to the masses and identities of the quarks, and like the masses themselves, they are free parameters of the standard model. Nobody knows why they take the values they do. For neutrinos, there is an analogous matrix called the PMNS matrix, named after Pontecorvo, Maki, Nakagawa, and Sakata. This matrix describes how neutrino flavor states mix with neutrino mass states, and it determines the probabilities of neutrino oscillation. It also contains mixing angles and phases that are free parameters. Interestingly, the mixing patterns for neutrinos are very different from those for quarks. The quark mixing angles are small, meaning quarks mostly stay within their own generation when they interact. The neutrino mixing angles are large, meaning neutrinos mix dramatically between generations. Why the patterns are so different is yet another unexplained feature of the standard model. All of these parameters, the masses, the mixing angles, the phases, are clues. They are data points that any deeper theory must explain. A true theory of mass would not just explain the mechanism by which mass arises, it would predict the values. It would derive the electron mass, the top quark mass, the neutrino masses, the mixing angles, all from some deeper principle. Finding such a theory is one of the grand challenges of fundamental physics. Some physicists believe the answer lies in grand unification. Grand unified theories attempt to merge the 3 forces of the standard model, the electromagnetic, weak, and strong forces, into a single force at very high energies. In some of these theories, the relationships between different particles become more constrained. Quarks and leptons are placed in the same mathematical structures, which can relate their masses and mixing angles. Some grand unified models predict specific relationships between quark masses and lepton masses, relationships that could, in principle, reduce the number of free parameters. But grand unification has its own challenges. The unification scale is extremely high, roughly 10 to the 16 giga-electron-volts, far beyond the reach of any foreseeable accelerator. Direct experimental tests are limited. The most dramatic prediction of many grand unified theories is proton decay. The idea that protons are not perfectly stable, but eventually decay into lighter particles. Experiments have searched for proton decay for decades using massive underground detectors filled with thousands of tons of water. They have never observed it. This does not rule out grand unification, but it constrains many models severely. Other physicists look to extra dimensions of space as a possible explanation. In some models with extra dimensions, the different generations of particles correspond to different standing wave patterns in the extra dimensions, much like the harmonics of a vibrating string. The masses of the particles would then be determined by the geometry of the extra dimensions. Different shapes and sizes of extra dimensions would give different mass spectra. This is an appealing idea because it connects particle masses to geometry, potentially explaining the seemingly arbitrary numbers through the structure of space itself. But, like grand unification, extra-dimensional models remain untested. The extra dimensions, if they exist, must be extremely small, and their effects are beyond current experimental reach. String theory offers perhaps the most ambitious framework for addressing the mass puzzle. In string theory, all particles are different vibration modes of tiny fundamental strings. The masses of particles are determined by how the strings vibrate, which in turn depends on the geometry of the extra dimensions in which the strings propagate. In principle, string theory could predict all the masses and coupling strengths of the standard model from the geometry of a single compact space. The dream is that there is one correct geometry, one specific shape of the extra dimensions, and from that shape, all the parameters of particle physics flow. But in practice, string theory faces the landscape problem. There are an enormous number of possible geometries for the extra dimensions, perhaps 10 to the 500 or more. Each geometry gives a different set of particle masses and coupling strengths. Most of these would produce a universe very different from ours. Without a principle that selects the right geometry, string theory can accommodate almost any set of particle masses rather than predicting specific ones. This is the challenge that has occupied string theorists for decades and remains unresolved. Let me now turn to what experiments might tell us in the coming years and decades. Because while the theoretical landscape is uncertain, the experimental program is rich and active. The most immediate opportunity involves precision measurements of the Higgs boson itself. The LHC continues to operate, collecting more data with every run. An upgraded version, the high luminosity LHC, is planned to begin operations in the late 2020s. This upgrade will increase the rate of collisions dramatically, producing roughly 10 times more data than the current machine over its lifetime. With this data, physicists will measure the Higgs boson's properties with unprecedented precision. They will measure how often the Higgs boson decays into different particles, how strongly it couples to the top quark, how strongly it couples to the bottom quark, how strongly it couples to the tau lepton, how strongly it couples to the W and Z bosons. Each of these measurements tests the standard model's predictions. Any deviation, even a small one, would be a sign of new physics. The Higgs boson could be the portal through which new physics first reveals itself. If the Higgs boson couples to unknown particles, if there are additional Higgs bosons, if the Higgs is composite rather than fundamental, all of these possibilities would show up as deviations from standard model predictions in precision Higgs measurements. The deviations might be small, perhaps a few percent, but with enough data, they could be detected. Beyond the LHC, several proposals exist for future colliders that would study the Higgs boson with even greater precision. The most developed proposals include the FCC, the Future Circular Collider at CERN, which would be a roughly 100-kilometer ring capable of colliding electrons and positrons at the Higgs production threshold with extraordinary precision. The CEPC, the Circular Electron-Positron Collider, proposed in China, has similar goals. CLIC, the Compact Linear Collider, would use a different technology. The ILC, the International Linear Collider, proposed in Japan, would also produce Higgs bosons in a clean environment ideal for precision measurements. These machines are sometimes called Higgs factories because their primary purpose would be to produce millions of Higgs bosons and study their properties with a level of precision far beyond what the LHC can achieve. Electron-positron collisions are much cleaner than the proton-proton collisions at the LHC, producing far less background noise and allowing much more precise measurements. A Higgs factory could measure Higgs boson coupling strengths to better than 1% precision in many channels. At this level of precision, even tiny effects from new physics could become visible. What makes a Higgs factory so powerful is not just the volume of data, but the cleanliness of the environment. At the LHC, protons collide with protons. Protons are composite objects, bags of quarks and gluons, so every collision is messy. The Higgs boson is produced in a spray of other particles, and disentangling the signal from the background requires sophisticated statistical techniques. The measurements are impressive, but they are limited by this inherent messiness. At a Higgs factory, using electron-positron collisions, the situation is fundamentally different. Electrons and positrons are point particles. The collision is clean. You know exactly how much energy went in, and you can account for exactly what came out. The Higgs boson is produced in a well-defined initial state, and its decay products can be measured with far less ambiguity. This means measurements that are currently limited to 10 or 20% precision at the LHC could reach 1% or even sub-percent precision at a Higgs factory. At that level, you start to see things that are invisible at lower precision. If the Higgs boson couples to bottom quarks at 97% of the standard model prediction instead of 100%, that 3% deviation would be a clear signal of new physics. It might indicate an additional Higgs boson mixing with the known one, or new particles running in quantum loops that slightly modify the coupling, or a composite structure at higher energies. The deviation itself would be a clue, pointing toward the kind of new physics responsible. A Higgs factory would also search for exotic Higgs decays, cases where the Higgs boson decays into particles not predicted by the standard model. If hidden sector particles exist, particles that do not interact through the known forces but do couple to the Higgs field, the Higgs boson might occasionally decay into them. These events would show up as Higgs bosons that seem to disappear, decaying into invisible products that escape the detector. Measuring the rate of invisible Higgs decays with high precision would constrain or reveal the existence of such hidden sectors. The standard model predicts a tiny rate for invisible Higgs decays through the Higgs decaying into pairs of Z bosons, which then decay into neutrinos. Anything above that predicted rate would be new. The Higgs boson's coupling to itself is particularly important. In the standard model, the Higgs potential has a specific shape determined by the Higgs self-coupling, a parameter called lambda. Measuring this self-coupling directly would tell us about the shape of the Higgs potential and could shed light on the vacuum stability question. Is the universe truly metastable? Is the Higgs potential the simple quartic shape the standard model assumes, or is it more complex? Measuring the Higgs self-coupling requires producing two Higgs bosons simultaneously, which is an extremely rare process. The high luminosity LHC will make initial measurements, but a future collider would do much better. Neutrino experiments also promise significant progress on the mass question. Several large experiments are currently operating or under construction. DUNE, the Deep Underground Neutrino Experiment, will send a beam of neutrinos from Fermilab in Illinois to detectors in South Dakota, 1,300 kilometers away. By studying how neutrinos oscillate over this distance, DUNE will determine the ordering of neutrino masses, whether the third mass state is the heaviest or the lightest. This is called the mass hierarchy, or mass ordering, and determining it is a crucial step toward understanding the origin of neutrino mass. Experiments searching for neutrinoless double beta decay continue with increasing sensitivity. If neutrinos are Majorana fermions, their own antiparticles, this process should occur at some rate. Detecting it would reveal a fundamentally new type of mass, distinct from the Dirac masses generated by the standard Higgs mechanism. It would open a window into physics at energy scales far beyond what any accelerator can reach, because the seesaw mechanism links the tiny observed neutrino masses to extremely heavy particles at or near the grand unification scale. Cosmological observations also constrain neutrino masses. The total mass of all three neutrino types affects the large-scale structure of the universe, influencing how galaxies cluster and how the cosmic microwave background radiation looks. Current cosmological data sets an upper limit on the sum of neutrino masses at roughly 1/10 to 2/10 of an electron volt. Future surveys of galaxy distribution and more precise cosmic microwave background measurements will tighten this constraint, potentially detecting the neutrino mass sum directly rather than just setting an upper limit. Beyond specific experiments, there is a broader question that hangs over all of this. What kind of answer are we looking for? When physicists say they want to explain the values of particle masses, what would count as a satisfying explanation? One possibility is a calculable theory, a deeper framework that takes fewer inputs than the standard model and derives the masses as outputs. String theory aspires to this in principle. A grand unified theory could do this partially. Any such theory would reduce the number of free parameters, replacing mysterious numbers with calculated predictions. This would be the most satisfying outcome from a scientific perspective. You would understand not just how mass arises, but why it takes the specific values it does. Another possibility is that the values are environmental. In this view, the standard model parameters vary across different regions of a vast multiverse, and we observe the values we do because they are compatible with the existence of observers. The electron mass is what it is, not because any equation demands it, but because in regions where it was very different, atoms would not form, chemistry would not work, and no one would be around to wonder about it. This is the anthropic explanation, and it is deeply controversial. Many physicists consider it a last resort, an admission of defeat rather than an explanation. Others argue it might simply be the truth, uncomfortable as it is. A third possibility, more subtle, is that the masses are determined by some mathematical structure we have not yet recognized. Perhaps there is a symmetry, or a geometric principle, or a number-theoretic pattern that fixes the masses. Several physicists have noticed approximate relationships between particle masses. The quark masses roughly follow a geometric progression across generations, each generation roughly 10 to 50 times heavier than the last. The charged lepton masses show a similar but distinct pattern. These patterns might be coincidences, or they might be clues pointing toward an underlying structure. If someone found the right mathematical framework, the masses might suddenly fall into place like a decoded cipher. But despite decades of effort, no such framework has been convincingly identified. The honest answer, the one most physicists would give if pressed, is that we do not know what kind of explanation is correct. We do not know whether the masses will be calculated from a deeper theory, explained by environmental selection, revealed by a hidden pattern, or understood through some approach no one has yet imagined. This uncertainty is humbling. It is also exciting. It means there is genuine discovery waiting to be made. It means the story of mass is far from over. Let me close by reflecting on what the Higgs boson discovery actually means in the larger arc of physics. Because the tone of this story might suggest disappointment, and that would be the wrong takeaway. The discovery of the Higgs boson was not a failure. It was not a letdown. It was a monumental achievement. For nearly half a century, physicists predicted that a field permeating all of space gives mass to fundamental particles, and that an excitation of that field should be detectable as a new particle. They built the most complex machine in human history to test this prediction, and the prediction was confirmed. The particle was found exactly where the theory said it should be, with properties matching the standard model's predictions to every decimal place we can currently measure. That is an extraordinary triumph of human intelligence. It is one of the greatest confirmations of a theoretical prediction in the history of science. But it is a triumph that illuminates, rather than eliminates, mystery. The Higgs mechanism is real, and it is essential. Without it, the electroweak theory would not work. The W and Z bosons would be massless. The weak force would have infinite range. Atoms, as we know them, could not exist. The universe would be unrecognizable. The Higgs field is a necessary part of the machinery that makes the universe the way it is. But it is not sufficient. It does not explain why particles have the masses they have. It does not explain why protons are heavy. It does not explain why neutrinos have mass. It does not explain its own mass, or the puzzling fine-tuning that mass seems to require. It confirmed a mechanism, but revealed a horizon of ignorance beyond that mechanism. This is how science works at the frontier. Each answered question reveals new questions. Each discovery opens new mysteries. Each step forward shows you how much farther there is to go. The Higgs boson did not complete the picture of mass. It confirmed one piece and revealed how much of the picture remains blank. Mass, the most familiar property of matter, the thing you feel every time you lift an object or take a step, remains one of the deepest open questions in fundamental physics. We know how mass arises for certain fundamental particles. We know how mass arises for composite particles like protons. We know that neutrinos have mass through some unknown mechanism. But we do not know why any of these masses take the values they do. We do not know why the Higgs boson is as light as it is. We do not know whether there is a single, unified explanation waiting to be discovered, or whether mass will turn out to be an irreducibly complex phenomenon with multiple independent origins. There is something philosophically striking about where we stand. For centuries, physics progressed by unifying seemingly different phenomena under single explanations. Newton showed that the force pulling an apple from a tree and the force holding the moon in orbit are the same force. Maxwell showed that electricity and magnetism are two aspects of one field. Einstein showed that space and time are interwoven into a single fabric. The Standard Model showed that the electromagnetic force and the weak nuclear force are branches of the same underlying interaction. Each unification simplified the picture. Each one replaced two mysteries with one deeper understanding. Mass resists this pattern. Instead of converging toward a single explanation, mass seems to fracture into multiple phenomena the closer you look. Fundamental particle masses come from one source. Composite particle masses come from another. Neutrino masses come from yet another. The values of these masses are unexplained. The Higgs sector that generates some of them is itself mysterious. The deeper you dig, the more questions you find. This might mean we have not yet found the right unifying framework. Perhaps there is a theory that ties all of these threads together, a single principle from which the Higgs potential, the QCD scale, the neutrino mass mechanism, and the values of all the Yukawa couplings all follow. Such a theory would be one of the greatest intellectual achievements in human history. Or it might mean that mass is genuinely composite, not in the sense that particles are made of smaller parts, but in the sense that what we call mass is an umbrella term for several distinct physical phenomena that happen to produce the same macroscopic effect. Either answer would be profound, and either answer remains possible. What we do know is that the universe cares about mass. Mass determines which particles are stable and which decay in fractions of a second. Mass determines the size of atoms, the energy output of stars, the structure of the periodic table, and the chemistry that makes life possible. If the masses of the quarks were slightly different, protons might be unstable and atoms could not exist. If the electron were much heavier, atoms would be smaller and chemistry would change dramatically. If neutrinos were massless, certain processes in the early universe would have proceeded differently, potentially affecting the formation of galaxies and stars. The specific values of particle masses are not arbitrary details. They are part of the blueprint of a universe that allows complexity, chemistry, and life. Consider how delicately this balance works. The proton is slightly lighter than the neutron. The difference is tiny, only about 1.3 mega-electron volts, roughly 1/7 of 1% of the proton's mass. But this small difference is why the universe looks the way it does. Because the proton is lighter, a free neutron can decay into a proton, but a free proton cannot decay into a neutron, Protons are stable. This is why hydrogen exists, why stars have fuel, why the periodic table begins where it does. If the down quark were lighter relative to the up quark by just a few mega-electron volts, the situation would reverse. Neutrons would be stable, and protons would decay. Hydrogen atoms could not exist because their nuclei are single protons. Without hydrogen, there would be no water. Without hydrogen, stars like the Sun could not ignite because stellar fusion begins with hydrogen. The universe would be a profoundly different and almost certainly lifeless place, all because of a quark mass shift smaller than 1%. The electron mass matters just as critically. Electrons orbit atomic nuclei at distances determined by their mass. A heavier electron would orbit closer, making atoms smaller and changing the way atoms bond with each other. The intricate molecular structures that underpin biology, the double helix of DNA, the folding of proteins, the chemistry of metabolism, all depend on atoms bonding at specific distances with specific energies. Change the electron mass by a factor of a few, and molecular chemistry as we know it ceases to function. Molecules that life depends on could not form or would not be stable. Even the absolute scale of neutrino masses matters cosmologically. Neutrinos are the second most abundant particles in the universe after photons. If their masses were significantly larger, their gravitational influence in the early universe would have smoothed out the density fluctuations that seeded galaxy formation. Galaxies might never have formed, or might have formed much later and much differently. The large-scale structure of the cosmos, the web of galaxy clusters and voids we observe today, is sensitive to the total mass of neutrinos at a level that current cosmological surveys are beginning to probe. The fact that we cannot yet explain these values is not a source of despair. It is a source of motivation. Somewhere in the gap between what the Higgs mechanism explains and what remains mysterious lies new physics. New particles, new forces, new symmetries, new principles. Something we have not yet imagined. The history of physics is filled with moments where an incomplete explanation led to a deeper understanding. Newton's gravity explained the orbits of planets, but could not explain why gravity worked the way it did. Einstein's general relativity provided that deeper explanation, revealing gravity as the curvature of space-time. The Standard Model explains how mass arises, but cannot explain why it takes the values it does. Whatever comes next will provide that deeper understanding. The Higgs boson was not the end of the story of mass. It was the confirmation that the story is real, that the questions are the right questions, and that the answers are out there waiting. Every proton in your body carries mass that the Higgs field barely contributes to. Every neutrino passing through you right now has mass that the Standard Model cannot explain. The Higgs boson sits at 125 giga-electron volts, a value that seems to require either a miracle or a mechanism we have not found. Mass is the property that makes matter feel real. It is the reason the universe has structure rather than being a featureless wash of massless particles streaming at the speed of light. And it remains, after all our progress, one of the great unsolved puzzles of nature. The Higgs boson gave us a piece of the answer. The rest is still out there, waiting to be discovered.